Watch this. 9 out of 10 students literally throw away marks by writing generic everyday answers. So when asked about storage, saying something like, a USB is good because it's small, yeah, that's going to earn you exactly 0 marks. But take a look at the examiner standard response right next to it. See how it uses precise technical vocabulary? Words like non-volatile, data retention, and NAND flash durability? One is just a casual guess, while the other, that is a guaranteed mark. Let's diagnose this exam trap right now before you actually make it.
Welcome to this explainer. Today, we are going to completely upgrade your Cambridge IGCSE exam responses, taking them from those generic guesses to precise mark scheme-aligned answers. We're going to break down the exact traps that catch students out year after year and give you the visual frameworks you need to secure those full marks.
Okay, here's our roadmap for today. 1. Mastering flowcharts and pseudocode. 2. Decoding div and mod. 3. Hardware and storage secrets. 4. Risks and embedded systems. And 5. Final exam mark upgrades. Let's dive right into this.
Starting off with Section 1, Mastering Flowcharts and Pseudocode. Specifically, where algorithm logic usually just completely falls apart. So, flowcharts. They're the absolute building blocks of algorithm design, but man, they're a total minefield for easy mistakes. Notice the correct shapes here. You've got your ovals for start and end, rectangles for processing, and diamonds for making decisions. But what's really interesting is this mistake clinic at the bottom. It highlights some pretty catastrophic errors, like the dreaded infinite loop. Let's actually break down those catastrophic errors, because examiners will instantly dock your marks for these. First up, using the wrong symbol for an input or output. Remember, parallelograms, not rectangles, are for inputs. Second, forgetting to initialize your variables before the loop even starts. Classic trap. And third, the infinite loop. Look, if your loop structure forgets to initialize the variable at the start, or it fails to increment the counter inside the loop, the logic just breaks. The program will literally run forever. And that brings us to a really critical difference in iterative logic. You have to choose the right loop depending on when the condition actually needs to be tested. A precondition loop, like while do, tests your counter at the very start of the loop, meaning if the condition isn't met right away, the loop might not run at all. On the flip side, a post-condition loop, like repeat until, tests the counter at the end. That guarantees the loop is going to run at least once. It is a subtle structural difference for sure, but it completely dictates the flow of your pseudocode.
All right, moving to Section 2, Decoding div and mod. We're getting into mathematical operators, which is an area full of hidden traps.
The crucial point here is captured perfectly in the bus problem, which visually separates standard division, integer division, and modulus. See, when you're writing pseudocode, standard division often just doesn't cut it for real-world logistical problems. You absolutely need to know exactly when to use div and when to use mod. Let's walk through this bus analogy.
Just follow this step-by-step logic, and you'll guarantee you know exactly when to extract the quotient versus the remainder. Imagine you've got 230 students, and each bus holds exactly 52 seats. Standard division gives you 4.42 buses. But you obviously can't order 0.42 of a bus, right? So this is exactly where div comes in. 230 div 52 gives you exactly 4 whole buses. Easy. But what about the kids left behind? That's where mod steps in. 230 mod 52 identifies the remainder, telling us precisely that 22 students are left over and still need a ride. So remember, div is for whole units, and mod is for the remainder. But hey, be incredibly careful here. This is a massive exam trap when it comes to programming syntax. Do not confuse the / with the backslash if you are writing visual basic integer division. Standard division uses the /, but integer division, which is your div equivalent in VB, requires the backslash. It's a tiny, tiny visual difference, but I promise you examiners look for it specifically.
Okay, shifting gears to Section 3, Hardware and Storage Secrets. Let's dissect secondary storage. Look closely at Zone 1 and Zone 2 here to contrast the physical mechanisms of optical pits and LANs against a solid-state floating gate. An optical disc, like a CD or a Blu-ray, relies on a laser reflecting off physical bumps, called pits, and flat areas, called LANs, to represent binary zeros and ones. But a USB flash drive, it has no moving parts at all. It relies entirely on trapping electrons. You'll want to memorize this exact technical definition. Non-volatile memory means it retains data even when the power is turned off. And why does it do that? Because a flash of electricity forces electrons through an insulator, trapping them in a floating gate. When the power drops, those electrons are just stuck there, keeping your data safely saved. Explaining that floating gate mechanism is exactly what upgrades your answer.
And this table brilliantly illustrates how you must match the specific storage media to its realistic use case. An exam question isn't just going to ask, what is optical storage? No, it's going to ask you to recommend a storage type for a specific scenario. CDs use a standard red laser, perfect for audio. Blu-rays use a higher density blue laser, perfect for HD movies or modern console games. And USB flash drives? Their durable electronic floating gates make them the absolute ultimate choice for portable backups.
Moving right along to Section 4, Risks and Embedded Systems. Focus here is on explaining cybersecurity and control without sounding generic.
The foundational idea here is the layering your knowledge pyramid. This is all about pushing you past everyday language and into structured, technical vocabulary. When answering questions about internet risks, you can't just say, a hacker steals your data. You have to start with the everyday concept, elevate it by using the exact technical term, like malware or protocol, and then finally deliver an exam-shaped response that actually explains the core mechanism.
So, when you're dealing with malware or network protocols, just follow this exact sequence. Name it, explain how it works step by step, and explicitly tie it to the scenario. First, identify. What is it? Second, sequence. How does it work logically? And third, apply contextual specificity. Why is it being used here in this specific app? If the exam question is about a banking app, don't just explain encryption in a vacuum. Explain how encryption specifically protects the customer's financial data during transmission.
Okay, let's dive into embedded systems. This is an area where you explicitly need to learn the differences between similar concepts to avoid common errors. For example, logic processing makes decisions based on conditions, like checking if a value is true or false. Arithmetic processing, however, is strictly mathematical calculations. Mixing these up when you're describing a real-world device is a classic wrong turn. The overarching rule here is specificity over generic labels. You must anchor every single answer to the digital problem, whether that's an industrial robot or a smartphone. If the exam asks about an embedded controller in a washing machine, your answer absolutely has to talk about water level sensors and motor actuators. If it asks about a drone, you talk about GPS sensors and rotor control. Never, ever name a device without explaining exactly how its hardware or software works to solve that specific problem. And finally, Section 5, Final Exam Mark Upgrades. Before we wrap up, let's consolidate these strategies into actionable templates you can use right away. Let's do a fast interactive challenge. Can you instantly distinguish between these two easily confused data checks? Take a second. Think about your definition for validation and your definition for verification. Do you actually know the difference, or do they kind of just blur together in your head?
Never confuse these two in your exam. Validation ensures the data fits the rules, while verification just makes sure it was copied correctly. Validation is an automated check by the computer. It's asking, is this data reasonable? Is it within the allowed range? Like, a month cannot be the number 13, right? Verification, however, doesn't care about the rules at all. It just asks, does this data perfectly match the original source it was copied from? Like when you have to type your password twice to make sure you didn't make a typo.
Check this out. Use this 4-part answer template to guarantee you are satisfying command words like explain and describe to their absolute fullest. This is literally your golden ticket for high-mark questions. Start with a precise technical definition. Next, detail the physical mechanism or step-by-step software process. Then, directly apply it to the scenario given in the prompt. And finally, state the specific advantage or consequence of using that technology. If you hit all 4 of those, the examiner has no choice but to give you full marks. So analyze your own weak points, apply this exact framework to your next practice paper, and really ask yourself, are you truly explaining the mechanism or just stating generic facts? State means giving a quick, concise definition. Describe means laying out the features, but explain means showing the actual mechanism, the how and the why. Take these visual frameworks, look at a past paper today, and go upgrade your answers. Thanks so much for joining me on this explainer. Now, which topic are you going to conquer first?